Good morning, students. I am Pradeep Kumar Verma from Electronics and Communication Engineering Department of Ashoka Institute of Technology and Management, Varanasi. Today, we are here to discuss the topic IIR filter design, and in particular, we will discuss about Butterworth filter design. And first of all, we will discuss about the ideal low-pass filter. How does its magnitude response appears? So as we can see here in the diagram, the magnitude response of low pass filter. As the name suggests, the ideal low pass filter will pass the frequencies which are below a certain cutoff frequency, which is denoted by Fc, and will stop all the frequency signals higher than the cutoff frequency. Next, as we know that ideal response of the filter is not possible, so we can only approximate the ideal response, and in this slide we are going to discuss that. As we can see in the diagram, the maximum magnitude of the filter is 1, and it decreases after frequency fp to 0 at frequency fs. The frequency fp is called the passband H frequency. The frequency Fs is called the stop band H frequency, and the frequency in between Fp and Fs is called the 3 dB cutoff frequency. And the region between Fp and Fs is called the transition frequency band. Now we will discuss some features of Butterworth low pass filter. The magnitude response of the Butterworth low pass filter is shown in the diagram. As we can see, where as जो the maximum magnitude of the Butterworth filter is set to 1, and ohm c is the cutoff frequency, and we can see different color characteristics depending upon the order of the filter. N is nothing but the order of the filter. If we go on increasing the order of the filter, the Butterworth filter approximates the ideal response as can be seen from the given figure. Here we will discuss Butterworth filter approximation in the figure. We have some terms that we will use in designing of the Butterworth filter. First of all, on frequency axis, that is ohm, we have passband H frequency ohm P, the stop band H frequency ohm S, and the cutoff frequency ohm C. The cutoff frequency will be in between ohm P and ohm S. Now we have stop band attenuation, that is denoted by AS, and passband attenuation, that is denoted by AP. So the Butterworth low-pass filter magnitude response can be formulated as we can see in the formula, mod of H omega square is equal to 1 upon 1 plus ohm by ohm C whole power 2n, where n is the order of the filter, ohm C is the cutoff frequency. Now, as we discussed in the previous slide, AP is the attenuation in passband, AS is the attenuation in stop band, ohm P is the passband H frequency, ohm C is the cutoff frequency, ohm S is the stop band H frequency. So now we will discuss how we can design step by step the Butterworth low pass filter, and we also know that we have already discussed about the various transformation techniques that can be used to transform analog filter into digital filter. So first we discussed impulse invariant technique, then we later on discussed bilinear transformation, and both techniques can be used for transformation of analog filter to digital filter. So if we are using impulse invariant method, then we will use formula uh, ohm is equal to omega by ts, where ts is the sampling frequency. For Bayesian transformation, we use the formula ohm is equal to 2 by ts tan omega by 2, where uh, ohm is the frequency of analog filter, omega is the frequency of digital filter, and ts is the sampling time. Now step 2 is for calculating the order of the filter. We will use this formula for calculating the order of the filter. N is equal to 1 by 2 into log of 1 upon as square minus 1 upon 1 upon ap square minus 1 whole upon log of ohm s by ohm p. If the specifications are given in decibels, like stop band attenuation and passband attenuation, then we will use this formula, that is n is equal to 1 by 2 log of 10 to the power point 1 as will be in dB minus 1 upon 10 to the power point 1 ap, which will be also in dB minus 1 upon log of ohm s by ohm p. Third step will be the calculation of cutoff frequency ohm c. For impulse invariant method, we will use ohm c is equal to omega c by ts, and for Bayesian transformation we will use ohm c is equal to 2 by ts tan omega c by 2. Now for calculating ohm c, we will use ohm p upon 1 by ap square minus 1 whole to the power 1 upon 2n, and if the specifications are in dB, we will use ohm c is equal to ohm p upon 10 to the power point 1 ap will be in dB minus 1. Then we will calculate the poles. Poles will be calculated according to the formula Pk. Pk will represent the poles. Pk is equal to plus minus ohm c e to the power j n plus 2k plus 1 into pi by 2n, where k will be from 0, 1, 2 up to n minus 1. We will put the values of k 1 by 1 from 0 to n minus 1, and we will find the values for uh, poles. Then we can write the transfer function as follows. This will be the analog transfer function of the filter. Hs is equal to ohm c to the power n whole upon s minus p1, s minus p2 up to s minus pn minus 1. And if the poles are complex conjugates, then we have Hs is equal to ohm c to the power n upon s minus s1 into s minus S1 conjugate into S minus S2 into S minus S2 conjugate. The step 4 will be uh, design the digital filter using impulse invariant method or Bayesian transformation. That is, we will transform this analog filter transfer function into the digital filter transfer function by using any one of the techniques, transformation techniques that we have discussed earlier. Thank you.